45 days ago, someone at NASA opened a file they weren't supposed to see yet. High-resolution Hubble images of an object that wasn't following the rules. An interstellar visitor with metal where there should be ice, jets that ignore physics, and a composition that shouldn't exist naturally. Today, November 19th, 2025, at 3 p.m. Eastern, they're finally showing us what they've been staring at all this time. 3I Atlas, the third confirmed visitor from beyond our solar system, and possibly the strangest thing we've ever watched pass through our cosmic neighborhood. So settle in, because by the end of this, you'll understand exactly why NASA needed 45 days to figure out what to tell us, and why some scientists are quietly asking if this thing was ever a comet at all. The clock reads 3 p.m. Eastern Standard Time on November 19th, 2025, and somewhere inside NASA's Goddard Space Flight Center, a room full of scientists is about to show you something they've been holding for 45 days. 45 days. That's how long they've had high-resolution Hubble images of an object that shouldn't exist, doing things it shouldn't do, made of materials it shouldn't have. And today, finally, we get to see what they've been looking at. The object has a name that sounds like it belongs in a filing cabinet. 3I Atlas. But don't let the bureaucratic designation fool you. This thing is only the third confirmed interstellar object humanity has ever detected. The third visitor from beyond our solar system that we've actually managed to spot and track. Think about that for a moment. In all of human history, with all our telescopes pointed at the sky, we've confirmed exactly 3 objects that came from somewhere else. 3I Atlas is number 3. It was discovered back in July of 2025, and from the moment astronomers first calculated its trajectory, they knew something was different. The object is traveling on what's called a hyperbolic orbit. That's the mathematical way of saying it's not stuck here. It's not bound to the sun. It came from somewhere out there in the galaxy. It's passing through our neighborhood at a staggering 137,000 miles per hour, and it's never coming back. It reached its closest approach to the sun on October 30th, 2025, getting within about 1.4 astronomical units. That's roughly the distance between Earth and Mars, if you're keeping score at home. NASA's preliminary data suggests the nucleus of this object could be anywhere from 440 meters across to 5.6 kilometers. That's a huge range of uncertainty, which tells you something right there. They're not sure what they're looking at. The smaller estimate makes it about the size of a large skyscraper. The larger estimate makes it a mountain hurtling through space at incomprehensible speed. But size isn't what's keeping scientists up at night. It's the anomalies. And there are several. First, there's the composition. Preliminary briefings, the kind that leak out before press conferences, mention something unusual. A nickel-rich composition. Not just nickel present, but nickel possibly exceeding iron content. If you know anything about how cosmic chemistry works, that sentence should make you sit up straight. Comets don't do that. Asteroids don't typically do that. The universe makes nickel and iron together in the hearts of dying stars, and they come out in predictable ratios. An inversion where nickel dominates is genuinely weird. Second, there's water. Or rather, there isn't much. Comets are supposed to be dirty snowballs, full of water ice that sublimates as they approach the sun, creating those beautiful tails we all recognize. 3I Atlas doesn't seem to follow the script. Reports suggest its water content is surprisingly low. Not absent, but far less abundant than what you'd expect from a typical comet. So what exactly is this thing sublimating to produce its activity? Third, and this is where it gets truly strange, there are the jets. Twin jets, to be precise. Stable, symmetric, and apparently unaffected by the object's rotation. Comets usually spin, and when they spin, their jets move. The vents on the surface rotate in and out of sunlight, turning on and off like cosmic sprinklers. But 3I Atlas seems to have jets that just stay there, pointing in consistent directions, defying what rotation models would predict. Now let's talk about that 45-day silence. NASA captured these Hubble images back in July. It's now mid-November. What takes 45 days to verify? The official explanation, if you ask agency representatives, involves calibration issues. Hubble's instruments need careful analysis, especially when you're looking at a faint, fast-moving object. There are red channel corrections to apply, color curves to verify against ground-based observations, polarization data that might not match initial expectations, noise in those early July exposures that needs filtering out. That's the charitable interpretation, the one that assumes NASA is just being responsible, crossing every T and dotting every I before releasing data that could change our understanding of interstellar objects. But there's another interpretation, and it's been spreading through online astronomy communities like wildfire. Why would NASA sit on dramatic images for nearly 2 months unless those images showed something they weren't sure how to explain? Unless internal debates were happening about what those images actually revealed? Unless there was concern, legitimate or otherwise, about how the public and media would react. Some people are already using the phrase alien probe in connection with 3i Atlas. It's out there now, circulating in forums and comment sections, fueled by every day that passed without NASA releasing the full data. The agency has experience with this kind of speculation. They remember what happened with Oumuamua, the first confirmed interstellar visitor back in 2017. That object's unusual acceleration led to papers speculating about light sails and artificial origins. NASA doesn't want a repeat of that media circus unless they're absolutely certain of what they're dealing with. So picture the position they're in. Release too early, and you risk misinterpretation. You risk headlines screaming about alien artifacts before you've properly ruled out natural explanations. Hold too long, and you fuel conspiracy theories. You look like you're hiding something, even if you're just being careful. It's a no-win situation, and 45 days suggests they chose the cautious route. Today's press conference is the end of that silence. Somewhere in that building in Maryland, there are scientists who've been staring at these images for weeks, arguing about what they mean, running models, checking and rechecking their assumptions. And in a few hours, we'll finally see what they've been seeing. The question you should be asking yourself right now is simple. What could those images possibly show that would require 45 days of verification? What features could 3i Atlas have that would make NASA's best and brightest scientists pause, debate, and carefully prepare their words before sharing with the world? By the end of this investigation, you're going to have enough information to form your own conclusion. Is 3i Atlas just a comet from another star system, following natural physics in slightly unusual ways? Or is it something else entirely? Something that doesn't fit our models because it was never meant to? The press conference starts in hours, but the real story started 45 days ago, when someone at Goddard first opened those Hubble files and realized they were looking at something that wasn't supposed to exist. Before NASA's official reveal, before the carefully prepared statements and peer-reviewed interpretations, there was the underground. There's always an underground. Astronomers talk to each other. Data gets shared in preliminary form. Communities of amateur researchers and professional scientists with loose lips start dissecting whatever fragments of information leak out before the big show. For 3i Atlas, that underground has been extraordinarily active. Spectral summaries that weren't quite official yet. Photometry data that somehow made its way onto astronomy forums. Fragments of analysis that people started piecing together like a jigsaw puzzle where half the pieces are still in the box. And what those pieces suggest is frankly bizarre. Let's start with the nickel situation, because it keeps getting stranger the more you look at it. Community analyses of the available spectral data show what's being called a nickel-iron inversion. In plain language, that means nickel appears to be overrepresented compared to iron. In a typical cosmic object, whether it's an asteroid or a comet nucleus or interplanetary dust, you expect iron and nickel to appear in ratios that reflect how they were made in supernova explosions. Iron usually dominates. Nickel is the supporting actor. But in 3i Atlas, that script appears to be flipped. Nickel is showing up stronger in the spectral signatures than anyone would predict for natural cometary material. This hasn't been confirmed by all teams yet. NASA will presumably address it today. But multiple independent analysts looking at the leaked data are seeing the same thing, which means either there's a systematic error everyone's making, or we're looking at genuine compositional weirdness. Then there's the hydroxyl problem. Spectroscopy of comets usually shows strong signatures of water molecules breaking down in sunlight. You see H2O directly, and you see its breakdown products like hydroxyl radicals. You also often see cyanogen, that's CN, and other molecular fragments. The ratio of these signatures tells you what kind of ices the comet contains. 3I Atlas is showing strong cyanogen signals in some observations, but the water lines aren't matching up proportionally. It's like finding smoke without quite enough fire. Something is producing those molecular radicals, but it's not the expected abundance of water ice doing it. Some researchers are suggesting the object might be rich in carbon monoxide or carbon dioxide ice instead, materials that sublimate more easily than water and could explain the activity without requiring massive water content. That's a natural explanation, and it might be correct, but it's still weird for an object we're calling a comet. Now, let's talk about the anti-tail. Multiple observers, both professional and amateur, have reported something that doesn't make geometric sense at first glance. Comet tails point away from the sun, because solar radiation and the solar wind push material outward. That's basic comet physics. But 3I Atlas has been showing a persistent jet that appears to point toward the sun. It's sometimes called a countertail or anti-tail, and while there are optical effects that can create the illusion of sunward-pointing features, multiple independent observations suggest this is a real physical jet of material streaming in the wrong direction. That's not impossible in comet physics. You can get complex gas dynamics near the nucleus that create unusual geometries. But it's uncommon, and combined with everything else, it adds to the pile of things that don't quite fit the standard comet template. The rotation models are failing too. Astronomers use photometry, measuring how bright an object appears over time, to figure out how fast it's spinning and in what orientation. When you combine rotation data with observations of where the jets are pointing, you should be able to build a consistent model. The jets are tied to active regions on the surface, so as the object spins, those jets should move, should turn on and off, should show predictable patterns. For 3I Atlas, the models keep breaking. The thrust vectors appear too stable. The jets seem to stay pointing in roughly the same directions, regardless of what the rotation should be doing. Multiple research teams have tried to reconcile this, and the fits aren't working. Either the rotation is far more complex than the photometry suggests, or something else is stabilizing those jets in ways that natural comet physics doesn't easily explain. And then there's the wow signal coincidence, which is probably nothing, but it's too delicious for the internet to ignore. Back in 1977, the Big Ear radio telescope detected a strong, unexplained radio signal from the constellation Sagittarius. It lasted 72 seconds, was never detected again, and became one of the most famous mysteries in the search for extraterrestrial intelligence. Someone with too much time and a decent astronomy program noticed that the arrival vector of 3I Atlas, traced backward into interstellar space, lies within about 9 degrees of the direction that wow signal came from. 9 degrees is not particularly close in astronomical terms. The odds of random coincidence are actually not that low when you're dealing with the whole sky. But in a year where people are already primed to ask whether 3I Atlas might be artificial, that directional overlap is catnip for speculation. Forums are lighting up with people asking whether the wow signal might have been a transmission from whoever or whatever made this object billions of years ago. Is it reasonable to connect them? Almost certainly not. But the human brain loves patterns. And when you combine a famous unsolved mystery from 1977 with a weird object showing up in 2025 from roughly that direction, people are going to connect dots, whether those dots belong together or not. What's fascinating is how mainstream the speculation has become. This isn't just fringe conspiracy theorists anymore. You're seeing amateur astronomers with serious credentials, independent researchers with PhDs, and even a few vocal scientists saying openly that 3I Atlas deserves consideration as something potentially non-natural. Not definitely artificial, not probably artificial, but weird enough that ruling it out requires actual work. The public reaction has been intense. Reddit astronomy communities are dissecting every leaked spectrum. Twitter is full of both excitement and skepticism. YouTube channels are cranking out analysis videos faster than NASA can prepare their official statements. And underneath all of it is a current of genuine uncertainty. Nobody knows what to make of this thing yet. Which brings us back to NASA's 45-day silence. If the leaked data is even remotely accurate, then the agency has been sitting on images and measurements of an object that challenges multiple assumptions about cometary physics, an object with weird composition, unusual activity patterns, stable jets that defy rotation models, and low water content that makes you wonder what category it even belongs in. Maybe the delay was just responsible science. Calibration takes time. Cross-checking with ground observatories takes time. Making sure you're not about to embarrass yourself with bad data takes time. But maybe, just maybe, there were deeper debates happening inside those walls. Debates about how to present findings that don't fit existing frameworks. Debates about how much speculation to entertain in official statements. Debates about whether to use words like anomalous or unprecedented, or whether those words would trigger exactly the kind of media frenzy they're trying to avoid. Today we'll find out what they decided to say. But the leaked clues have already told us something important. Whatever 3i Atlas is, it's not behaving like the textbook examples we're used to. And that means either our textbooks are missing some exotic but natural edge cases, or we're looking at something that was never in any textbook to begin with. Imagine you're a scientist at Goddard Space Flight Center, and you've just pulled up the first high-resolution Hubble images of 3i Atlas. You're expecting a comet. Maybe an unusual one, given its interstellar origin, but fundamentally something that fits within the boundaries of what comets can be. And then you look at the data, and something is wrong. Not obviously wrong. Not screaming error message wrong. Just subtly, persistently, maddeningly off in ways that don't resolve when you check your calibrations. What do? You check again and again. And that's how 45 days disappear. Let's talk about what verification actually means for Hubble observations of a faint, fast-moving interstellar object. First, there are the instrument calibrations themselves. Hubble has been in space since 1990, and while it's been serviced and upgraded multiple times, its instruments still require careful calibration. The Wide Field Camera 3, which likely captured these images, has known quirks in its red channel response. When you're trying to measure the color of a faint object against the background sky, those quirks matter. You need to apply corrections. Compare against standard stars. Make sure the colors you're seeing are real and not artifacts of how the detector responds to different wavelengths. Then, there's the challenge of photometry on a moving target. 3i Atlas isn't sitting still. It's racing through the solar system at over 100,000 miles per hour. When Hubble locked onto it for those July exposures, the spacecraft had to track the object's motion, which means the background stars are trailing in the images. Separating the comet's light from the background, especially if it's faint and diffuse, requires sophisticated analysis. You're essentially doing forensic reconstruction on digital images to isolate what belongs to the comet and what's just noise or background contamination. Cross-checking with ground-based telescopes adds another layer of complexity. Multiple observatories worldwide have been tracking 3i Atlas since its discovery. They're using different instruments, different techniques, different atmospheric conditions. When NASA's space-based observations show something unusual, they need to verify whether ground-based observers are seeing the same thing. Do the color measurements match? Does the brightness evolution agree? Are the jets pointing in the same directions when you correct for viewing geometry? These cross-checks take time because you're coordinating between institutions, between countries, between teams with different data pipelines and analysis methods. Someone at Goddard has to compile observations from maybe a dozen different sources, standardize the measurements, account for systematic differences in how each telescope calibrates, and then try to build a coherent picture from all those puzzle pieces. Polarization adds yet another wrinkle. Some observations of 3i Atlas included polarimetry, measuring how the light from the object is polarized. This can tell you about the properties of dust grains in the coma, the cloud of gas, and dust surrounding the nucleus. But polarization measurements are notoriously tricky. They're sensitive to instrumental effects, atmospheric conditions, and the exact geometry of your observation. If your polarization data doesn't match your photometry data, you've got a problem that needs resolving before you go public. And then there's the noise issue. Those July exposures were taken when 3I Atlas was still fairly distant from the Sun, before its October 30th perihelion. That means the object was fainter, less active, harder to see. Extracting signal from noise in those conditions is an art form. You're using statistical techniques to pull real structure out of what might be just random fluctuations in the detector. Make a mistake here, and you could report features that don't actually exist, or miss features that do. All of this explains why responsible verification takes weeks, but it doesn't quite explain 45 days. For that, you need to consider the institutional memory of past mistakes. NASA remembers Oumuamua. That first interstellar visitor back in 2017 turned into a media circus when its unexpected acceleration led to speculation about artificial origins. The agency watched as respected scientists published papers suggesting light sails, watched as the public grabbed onto alien spacecraft narratives, watched as the careful work of ruling out exotic explanations got lost in the noise of viral headlines. They don't want that again, not without being absolutely certain of their ground. They also remember the lessons from earlier controversies. The Mars meteorite from 1996 that might have contained fossils, except it probably didn't. The pulsars initially mistaken for alien beacons back in the 1960s. The long history of astronomical phenomena that looked artificial until someone figured out the natural explanation. NASA's institutional culture has learned to be cautious, to triple check, to make sure they're not about to trigger global headlines based on data that might have simpler explanations once you look harder. But caution creates its own problems. The longer you wait, the more pressure builds. Leaks start happening because scientists talk to colleagues, and colleagues talk to students, and students post on forums. Speculation fills the vacuum where official information should be. Conspiracy theories gain traction because silence looks like secrecy. By the time you're ready to release your carefully verified data, the narrative may already be out of your control. There's also political and public pressure to consider. NASA exists on taxpayer dollars, and those taxpayers want answers. When you discover something potentially paradigm-shifting and then go silent for a month and a half, questions get asked. Why is the verification taking so long? What are they hiding? Is it really just calibration, or are there deeper issues they're not talking about? Inside Goddard, you can imagine the debates. One faction arguing for immediate release, transparency, letting the scientific community help interpret the data. Another faction arguing for caution, for waiting until every alternative explanation has been exhausted, for making sure the agency doesn't get burned by premature announcements. Both sides have valid points. Both sides are trying to do the right thing, but they're operating under different assumptions about what right means in this context. The scientists who want to release quickly are thinking about scientific openness, about the value of many eyes on interesting data, about the risk of appearing to suppress information. The scientists who want to wait are thinking about credibility, about the agency's reputation, about not wanting to be the person whose hasty announcement turned out to be based on a calibration error. What's really at stake here isn't just NASA's reputation, though that matters. It's the scientific value of getting the interpretation right. 3I Atlas could reshape our understanding of interstellar objects, of how comets form in other star systems, of what kinds of materials and structures are possible in the galaxy beyond our local neighborhood. But only if the data is solid. Only if the community trusts that what NASA releases has been vetted thoroughly enough that building theories on top of it won't be building castles on sand. So they took 45 days. They ran the calibrations, cross-checked with ground observations, analyzed the polarization, filtered the noise, debated the interpretations, and presumably reached some kind of internal consensus about what they could say with confidence and what remained uncertain. Today, we'll learn whether that consensus involves phrases like within normal parameters for an interstellar comet, or whether it involves more interesting words. Words like anomalous, or unexpected, or requires further study. The language NASA chooses will tell you everything about what those 45 days of internal debate concluded. But here's the thing that should make you uncomfortable. If NASA, with all its resources and expertise, needed 45 days to figure out what they were comfortable saying about 3I Atlas, what does that tell you about how weird this object actually is? There's a moment in science when the numbers stop adding up, and you realize you're either making a mistake or looking at something genuinely strange. For 3I Atlas, that moment involves jets, rotation, and physics that doesn't want to cooperate. Comets jet. That's what they do. As icy material on the surface heats up from solar radiation, it sublimates, turning directly from solid to gas without passing through liquid. That gas erupts from the surface, carrying dust particles with it, creating those visible jets and tails that make comets beautiful. The jets come from active regions, specific areas where ice is exposed or particularly accessible to sunlight. As the comet rotates, different regions swing into sunlight, and the jet activity changes accordingly. This is standard, well-understood comet physics. We've observed it on dozens of comets, modeled it extensively, used it to infer rotation rates and surface properties. It works, except on 3I Atlas, where it apparently doesn't. The jets on this object are described as twin jets, symmetric, stable. Multiple observations over several weeks show them pointing in roughly consistent directions. That's the first red flag, because rotation should be changing what we see. A comet's nucleus is essentially a tumbling chunk of ice and rock and dust, spinning on some axis at some rate. Even if the jets themselves are fixed to specific surface features, our view of those features should change as the object spins. We should see the jets move across our field of view, should see them brighten and fade as they rotate in and out of our line of sight, should see patterns that reflect the underlying rotation. Photometry data, the measurements of how bright the object appears over time, should reveal that rotation rate. When astronomers plot brightness versus time for a rotating object, they get a periodic curve. The shape and period of that curve tell you how fast it's spinning and what its shape is roughly like. For 3I Atlas, there are light curve analyses, some potentially using precovery data from TESS, the Transiting Exoplanet Survey satellite, which photographs huge swaths of sky and might have caught this object before anyone knew it was interesting. The problem is that when you take the rotation period suggested by photometry and try to match it with the observed jet behavior, the models fail. The jets are too stable. They don't move the way they should if the object is spinning at the rate the light curves suggest. You can try to invoke complex tumbling, wobbling rotation states, precession, all kinds of geometric gymnastics, but nothing quite fits. Let's think about what this means physically. If the jets are coming from fixed vents on the surface and they're staying pointed in consistent directions in space, then either the object isn't rotating much at all, which would contradict the photometry, or something is actively stabilizing the jet directions despite rotation. How could natural comet physics stabilize jets? One possibility is internal cavities or chambers. Imagine the nucleus isn't a solid chunk, but has internal voids, maybe created by past sublimation or structural weaknesses. Gas could accumulate in these cavities and then escape through specific channels that act like nozzles. If the geometry of those channels is just right, you might get jets that maintain consistent directions even as the surface spins around them. It's exotic, but not impossible. Another idea involves non-gravitational torques. The jets themselves carry momentum. When gas erupts from the surface, it pushes on the nucleus, exerting forces that can change the object's spin state over time. Usually this leads to complex evolving rotation, but under very specific conditions, maybe those torques could stabilize certain configurations. Maybe the mass loss from the jets is redistributing mass inside the nucleus in ways that damp out wobbles or maintain a particular orientation. Some researchers have proposed that radiation pressure from sunlight, combined with the object's shape and surface properties, could contribute to unusual dynamics. Light from the sun pushes on the object, not just creating tails, but exerting torques that depend on the shape and reflectivity of the surface. For a highly elongated or asymmetric object, these effects might be more pronounced than usual. But here's where you start running into problems with the numbers. Community analyses floating around online, the kind done by people with too much time and too much physics knowledge, suggest that the energy budget doesn't quite work. Sublimation of water ice, the most common comet volatile, releases a certain amount of energy per kilogram. That energy drives the gas expansion that creates jets. But if 3I Atlas is low on water, what's driving the jets? Carbon monoxide and carbon dioxide sublimate at lower temperatures and can produce activity farther from the sun, but they have different energy profiles. When you try to calculate the mass loss rate, the thrust force those jets would produce, and the acceleration that thrust would cause, some of the numbers reportedly don't add up naturally. The jets seem to be producing more stable thrust than simple sublimation physics would predict for an object this size with this rotation rate, at this distance from the sun. That's not definitive proof of anything weird. There could be factors we're not accounting for, properties of the nucleus we can't measure directly, physics happening beneath the surface that observations can't detect. But it's suspicious, and suspicion is how scientific revolutions often start. Now let's go to the speculative extreme, just to see where it leads. Suppose, purely as a thought experiment, that 3I Atlas isn't entirely natural. Suppose those jets aren't random vents, but engineered openings. Suppose something designed this object, billions of years ago, and those jets serve some purpose we don't understand. Propulsion, maybe. Attitude control? Communication. Broadcasting some signal we haven't detected yet, because we're not listening at the right frequency or with the right equipment. If you wanted to design a probe that could survive billions of years in interstellar space and still function, when it passed through a solar system, you'd need stabilization. You'd need ways to control orientation, to keep antennas or sensors or whatever pointed in useful directions. Chemical thrusters, maybe, venting material in controlled bursts to maintain attitude without spinning helplessly. Does 3I Atlas show signs of that? Not obviously. But the jet stability, the resistance to simple rotation models, the way the thrust vectors seem too consistent for purely natural processes, it's at least compatible with that hypothesis. Not proof, not even strong evidence, just compatibility, which is the first step toward a hypothesis becoming plausible. Of course, the counter-arguments are strong. Natural comet physics is incredibly diverse. We've seen comets do weird things before and eventually figured out natural explanations. Comet Churyumov-Gerasimenko, visited by the Rosetta spacecraft, had complex jet activity tied to its strange shape and internal structure. Comet Hartley 2 showed hyperactive regions where jets were far more powerful than expected. The universe is full of edge cases, and edge cases don't require alien engineers. But here's what should keep you awake tonight. The jet paradox is a technical puzzle with no easy solution currently on the table. Multiple teams have tried to build consistent models, and they're not succeeding. That could mean we need better data, which today's press conference might provide. It could mean our models of comet nucleus structure and volatile distribution are too simplistic, which is probably true. Or it could mean we're looking at physics that doesn't fit our frameworks because the object wasn't made by nature. The question isn't whether 3I Atlas has weird jets. The question is whether weird jets plus weird composition plus weird water content plus weird everything else adds up to natural or something else. And that's the equation NASA has been trying to solve for 45 days. Let's talk about nickel and why it's causing such problems for people. Trying to explain 3I Atlas as a normal interstellar comet. In the spectral data that's been discussed in pre-conference leaks and community analyses, nickel shows up stronger than it should relative to iron. This is the compositional inversion we've mentioned, and to understand why it's so troubling, you need to know where nickel and iron come from in the first place. Both elements are forged in stars. Specifically, they're produced in massive stars that end their lives in supernova explosions. During those explosions, nuclear reactions create heavy elements and blast them into space, where they become part of the interstellar medium, the gas and dust between stars. When new stars and planetary systems form from that enriched material, they inherit the elemental ratios that supernovae produced. Iron is abundant because the nuclear physics of stellar fusion favors it. Nickel is less abundant because it's harder to make. In our solar system, in meteorites, in asteroids, In every natural sample we've analyzed, iron dominates nickel by substantial margins. The ratio varies depending on the sample and its history, but the hierarchy is consistent. More iron than nickel, always. 3I Atlas appears to violate that hierarchy, or at least show unusually high nickel relative to iron. That's cosmically weird. It suggests either that this object formed from material with very different nucleosynthetic history than our solar system's material, or that something has preferentially concentrated nickel at the expense of iron, or that we're misinterpreting the spectral signals entirely. Let's explore the natural explanations first, because they deserve serious consideration. One possibility is that 3I Atlas formed in a star system with unusual metallicity. Metallicity, in astronomy, refers to the abundance of elements heavier than hydrogen and helium. Stars with different metallicities have different proportions of heavy elements, depending on how many generations of previous stars lived and died to enrich their birth clouds. If 3I Atlas comes from a very old system, formed from material that went through unusual nucleosynthetic processes, maybe its elemental ratios don't match ours. This connects to the cosmic noon hypothesis we'll explore more later. If this object is billions of years old, from the era when the galaxy was churning out stars at peak rates, its chemistry might reflect conditions very different from the relatively recent, relatively well-mixed environment where our sun formed 4.6 billion years ago. Another explanation involves surface processes. Maybe what we're seeing isn't representative of the object's bulk composition. Maybe there's a crust, a surface layer that's been altered by eons of cosmic ray bombardment, interstellar dust impacts, or chemical reactions in the cold vacuum of space. Nickel and iron can oxidize differently, sublimate differently, respond differently to radiation. Perhaps some process has created a nickel-enriched surface, while the interior remains more typical. Thermal processing is another angle. If 3I Atlas came from a system where its parent body was heated, differentiated, melted, and separated by density, nickel and iron can end up in different layers. Earth has an iron-nickel core, but the crust is depleted in those metals. If we're looking at a fragment from a differentiated body, maybe we're seeing a layer that happened to concentrate nickel. Some scientists have proposed that the low water content and unusual composition could be explained by a thick, insulating crust. Imagine a crust made of dust and organics and rocky material, covering ices beneath. Water sublimates slowly through this crust, while more volatile compounds like carbon monoxide or carbon dioxide escape more easily. The crust could also selectively concentrate certain metals at the surface while burying others. These are all reasonable ideas. They push the boundaries of what we normally see in comets, but they're not physically impossible. The universe is large, and in a large enough universe, even improbable things happen occasionally. But then there's the other interpretation, the one that makes traditional scientists uncomfortable and makes online communities excited. What if the nickel signature we're seeing resembles engineered material more than natural cosmic material? Industrial nickel alloys exist because humans have learned that nickel, when combined with other elements in specific proportions, creates materials with useful properties. Corrosion resistance, strength at high temperatures, magnetic properties, all kinds of engineering advantages. If you were designing a spacecraft meant to survive billions of years in interstellar space, you might choose nickel-rich alloys for your construction material. They'd resist corrosion in the sense that chemical weathering in space is minimal. They'd maintain structural integrity through temperature extremes. They might have other properties we can't guess at because we don't know what engineering priorities an alien civilization would have. This is wild speculation. It's important to be clear about that. There's no direct evidence that 3I Atlas is artificial, and composition alone certainly doesn't prove it. You can find unusual elemental ratios in natural samples, and we don't know enough about the diversity of planetary systems in the galaxy to say what's truly impossible versus just improbable. But the speculation isn't coming from nowhere. It's emerging from people looking at the totality of the evidence, the composition, plus the jets, plus the water deficit, plus the rotation anomalies, and saying that the natural explanations require an awful lot of special pleading. Each individual anomaly can be explained, maybe, but explaining all of them together requires you to accept that 3i Atlas is an outlier in multiple independent ways simultaneously. Online forums, particularly forums. Places where amateur astronomers and data enthusiasts congregate have been buzzing with analysis attempting to quantify just how unusual this combination of properties is. Some people are arguing that the nickel signature, if it holds up, is essentially diagnostic of processing. That natural cosmic chemistry just doesn't produce this ratio without some kind of extreme, specialized conditions that we haven't observed elsewhere. The counterpoint, and it's a strong one, is that we have an extremely limited sample size. We've visited a handful of comets up close with spacecraft. We've observed maybe a few hundred in detail from Earth. We've confirmed exactly 3 interstellar visitors, and this is only the third. Our understanding of what's normal for cosmic objects is based on a tiny, biased sample drawn from one corner of one planetary system in one galaxy. Claiming we know what interstellar comets should look like is hubris. Maybe 3i Atlas is just the first time we're seeing an example of a category we didn't know existed. Ancient, metal-enriched, low-water interstellar objects from old stellar populations. Give them a name, study more of them, and in 50 years, this might seem completely normal. That's the conservative scientific view, and it's not wrong to take it seriously. But conservative views don't explain why NASA needed 45 days to decide what to say about this thing. Conservative, easily explained objects don't generate this much internal debate, or this much leaked speculation, or this much public fascination. Something about 3i Atlas is genuinely challenging to the people whose job it is to understand these objects. The nickel problem sits at the heart of that challenge because composition is fundamental. You can explain weird jets with complex rotation. You can explain low water with unusual thermal history. But composition is about nucleosynthesis, about where the atoms came from and what processes made them. When the composition doesn't match expectations, you're questioning deeper assumptions about stellar evolution, galactic chemical enrichment, planetary formation. You're saying either our models of those processes are incomplete, or this object's origin story is more exotic than we've been imagining. There's also the possibility that the spectral interpretation itself is wrong. Spectroscopy is powerful, but not foolproof. You're looking at light that's been absorbed and re-emitted by atoms and molecules on or near the object's surface. The patterns tell you what elements and compounds are present, but those patterns can be complicated by temperature, by mixtures of materials, by geometry and scattering effects. Maybe what looks like a nickel excess is actually something else. Some combination of factors that produces a similar spectral signature without requiring unusual composition. That's what today's press conference might clarify. If NASA spent 45 days checking and rechecking their spectral analysis, they should be able to tell us whether the nickel signature is real or an artifact. If it's real, they should tell us what natural explanations they've considered and which ones seem most likely. And if they can't offer a natural explanation that satisfies them, that's when things get really interesting. Because here's the uncomfortable truth. If 3i Atlas has genuinely anomalous composition that can't be easily explained by known astrophysical processes, then keeping an open mind about artificial origins isn't pseudoscience. It's just following the data where it leads. You don't start with, "it must be aliens," but you also don't rule it out a priori, just because it makes you uncomfortable. The scientific method is supposed to be about evidence, not comfort. If the evidence points towards something weird, you're supposed to seriously consider weird explanations, not just the ones that fit neatly into existing frameworks. That's how discoveries happen. That's how paradigms shift. So the nickel question isn't just about elemental ratios. It's about how we do science when confronted with genuinely anomalous data. Do we stretch natural explanations as far as they can possibly go before considering alternatives? Or do we put alternative hypotheses on the table early and test them rigorously alongside the conventional ones? Different scientists will answer that differently, and those different answers are probably fueling debates inside Goddard right now. What we know for certain is this: composition matters. It's a clue about where 3i Atlas came from, how it formed, what it's made of, and potentially what it is. If that composition turns out to be as unusual as the leaked data suggests, then every explanation, from exotic natural processes to artificial origins, deserves scrutiny. Not belief, not assumption, but honest, rigorous scrutiny. And maybe that's what 45 Days of Silence was really about. Not hiding anything, not conspiracy, just NASA trying to figure out how to honestly present findings that don't have easy answers, in a world where easy answers are what people expect, and anything else triggers chaos. We're about to find out what they decided to tell us. Let's step back from the immediate mysteries and ask a bigger question. Where did this thing come from? Not just in terms of direction, but in terms of time. There's a research paper, the kind that gets written when scientists have more ideas than answers, proposing something extraordinary about 3I Atlas. The hypothesis comes from researchers including Eubanks and colleagues, and it suggests that this object might not just be old, but ancient. Not millions of years old, billions. Potentially originating from an era of the Milky Way's history called cosmic noon, a period roughly 9 to 13 billion years ago, when star formation in our galaxy was at its peak. Cosmic noon is exactly what it sounds like. The high point, the moment when the galaxy was churning out stars faster than at any other time in its history. The gas was denser. Supernova explosions were more frequent. The entire galaxy was a more violent, active, energetic place. Stars formed from that environment would have different properties than younger stars like our sun. Planets and smaller bodies forming around those stars would inherit different chemistry, different elemental abundances, different initial conditions. The kinematic evidence is what makes this hypothesis interesting. Kinematics is the study of motion, and when you carefully analyze how 3I Atlas is moving through the galaxy, not just its speed but its trajectory and how that trajectory relates to known stellar populations, you can make inferences about where it came from. According to the analysis, 3I Atlas's motion is consistent with stellar populations from the Milky Way's thick disk. The thick disk is an older component of our galaxy, distinct from the thin disk where the sun lives. It contains stars that formed earlier in galactic history, before the disk settled into its current flattened structure. Objects associated with the thick disk are typically older, metal-poor in the astronomical sense, and have different orbital characteristics than younger populations. If 3I Atlas really is associated with the thick disk, and if its trajectory suggests it's been wandering the galaxy for billions of years, then suddenly a lot of the weirdness starts making a different kind of sense. The unusual composition could reflect the different nucleosynthetic environment of the early galaxy. The low water content could be explained by formation conditions that favored other volatiles. The whole package of anomalies might not be anomalies at all, just the natural properties of an ancient object from a different era of cosmic chemistry. Think about what that would mean. This object could be older than Earth, older than our solar system. It could have been wandering through interstellar space since before the sun even formed. A cosmic fossil, a relic from the galaxy's youth that just happened to pass through our neighborhood in 2025, giving us a fleeting chance to study something that's been traveling for longer than our entire planetary system has existed. That's mind-blowing, even without invoking anything artificial. If 3I Atlas is a pristine sample from cosmic noon, then it's a time capsule. Its composition records conditions from an era we can only study indirectly through observations of distant galaxies whose light has taken billions of years to reach us. Having one of these ancient objects right here, close enough to observe with Hubble, close enough to potentially send spacecraft to, is an opportunity that might not come again in human lifetimes. The same research paper proposes something even more ambitious. Suppose we wanted to sample 3I Atlas, to actually collect material from it for laboratory analysis. Right now, we have spacecraft scattered throughout the solar system. Mars orbiters, Jupiter missions like Juno, JUICE heading to Jupiter's moons, Europa Clipper, the Psyche mission to a metal asteroid. None of these were designed to intercept 3I Atlas. But its tail, the stream of dust and gas it's leaving behind, extends across space. If the geometry works out, if one of these spacecraft passes through the tail's projected path, there's a non-zero chance of collecting particles. It would be accidental sampling, opportunistic science. You wouldn't get much material, and you wouldn't have instruments specifically designed for cometary analysis. But even a few dust grains captured by existing detectors could tell you something about composition, about whether the nickel signature is real, about isotopic ratios that would confirm or refute the ancient origin hypothesis. The geometry is tricky, and the odds aren't great, but it's not impossible. Spacecraft have serendipitously detected cometary material before. If NASA or other space agencies determined that one of their missions might cross the tail, you can bet they'd try to make those measurements. A few milligrams of pristine ancient material would be worth the effort. Now here's where the cosmic noon hypothesis creates an interesting tension with the artificial origin speculation. If 3I Atlas is natural and ancient, then its weirdness is explained by age and origin. You don't need aliens. You just need a galaxy that was different 9 billion years ago, making objects with properties we're not familiar with because all our reference samples are much younger. But if it's ancient and artificial, that raises completely different questions. Who made it? When? For what purpose? A probe launched 9 billion years ago would predate not just humanity, but probably any technological civilization we're aware of in our cosmic neighborhood. It would suggest that intelligence arose very early in the galaxy's history, that some species achieved spaceflight when the Milky Way was less than a quarter of its current age, and that whatever they built lasted long enough to still be functioning, or at least identifiable billions of years later. That's a staggering thought. It implies technology so robust, engineering so advanced, that it survives timescales longer than most stars live. It implies motivations we can barely comprehend, because why would anyone launch something meant to last billions of years? What message or mission could possibly justify that kind of investment? Or maybe it's not even meant to last. Maybe 3I Atlas is a derelict, the broken remnant of something that failed long ago, tumbling through space as a technological fossil rather than a functioning probe. Maybe its jets aren't propulsion, just leaking gas from ruptured tanks or damaged systems. Maybe the nickel is just leftover hull material, exposed after eons of micrometeorite impacts stripped away outer layers. These are the kinds of thoughts that keep scientists awake at night, and also get them accused of watching too much science fiction. But speculation is part of the process. You think through the possibilities, rank them by plausibility, and then design tests to distinguish between them. That's how you avoid tunnel vision. How you make sure you're not missing the right answer just because it seems unlikely. The cosmic noon hypothesis is elegant because it offers a natural explanation that's still exciting. You don't need to invoke aliens to make 3I Atlas interesting. You just need to accept that the galaxy has been making objects for billions of years longer than Earth has existed, and we're only now getting our first close looks at some of them. If today's press conference confirms the ancient origin hypothesis, if the kinematic analysis holds up, and the chemistry matches expectations for thick disk populations, then 3I Atlas becomes the oldest thing humanity has ever directly observed up close. Not the most distant, we see ancient galaxies billions of light years away. But the oldest object in terms of when it formed that we've actually had in our cosmic backyard, close enough to image with Hubble, close enough to study in detail. That's a discovery worth 45 days of verification. That's something NASA would want to get exactly right before announcing, because getting it wrong would be embarrassing, but getting it right would be revolutionary. So maybe the delay wasn't about hiding weirdness. Maybe it was about making sure they could confidently say, this thing is 9 billion years old, and here's how we know. That would be enough. That would rewrite textbooks all by itself, but it still wouldn't explain the jets. Step back one more time, all the way back, and look at 2025 as a whole. Because 3I Atlas isn't happening in isolation. This year is shaping up to be one of those moments when the universe reminds us how little we actually understand. Start with artificial intelligence and exoplanets. Transformer-based neural networks, the same architecture behind large language models, are now being trained on spectroscopic data from exoplanet atmospheres. The goal is to predict what molecules are present in the atmospheres of distant worlds based on the light that filters through them when they pass in front of their stars. And here's the kicker. In some cases, these AI models are making predictions that observers later confirm with JWST or other telescopes. The machines are learning to read alien atmospheres better than traditional analysis methods in certain contexts. That's unsettling in a productive way. It means we're approaching a future where AI might flag anomalies before human scientists even know to look for them. What if a neural network analyzing data from interstellar objects flags 3i Atlas as inconsistent with natural patterns? What if machine learning detects signatures of artificiality that human intuition would miss? We're not quite there yet, but we're close. Close enough that you can imagine a scenario within the next decade where an AI system says, "This object doesn't match any natural category I've been trained on," and that's your first hint that something extraordinary is passing through. The technology has implications beyond exoplanets. Apply it to spectroscopy of comets, asteroids, interstellar visitors. Train networks on everything we know is natural, and then use them as anomaly detectors. If 3i Atlas showed up in such a system, would it be flagged as an outlier? Probably. And what would that tell us? Then there are the fast radio bursts. These have been a mystery since their discovery. Brief, intense pulses of radio waves from distant galaxies that last milliseconds and carry enormous energy. In 2025, astronomers are detecting FRBs with structure on microsecond timescales. Variability so fast that current plasma physics models struggle to explain it. You need coherence mechanisms, ways to organize electromagnetic radiation at scales and speeds that shouldn't be possible in natural astrophysical environments. Some of these FRBs repeat. Some are one-offs. Some come from magnetars, neutron stars with insanely strong magnetic fields. But others don't have obvious sources, and the mechanisms remain contentious. The energy budgets are staggering. The coherence is puzzling. And every time someone proposes a natural explanation, a new observation comes along that doesn't quite fit. Sound familiar? Fast radio bursts and 3i Atlas have something in common. They're both phenomena where the data is outpacing our theoretical frameworks. They're both cases where scientists are being forced to say, "We don't know," more often than they'd like. And they're both topics where speculative explanations, including non-natural ones, are at least being discussed in professional contexts, even if most scientists remain skeptical. The pattern here is important. Science is hitting edges. Not because we're running out of things to discover, but because the nature of what we're discovering is changing. We're finding objects and events that don't fit neatly into existing categories. The universe is messier, more diverse, more surprising than the models we built based on limited samples from our local neighborhood. 3i Atlas fits into that pattern perfectly. It's one more thing that makes scientists scratch their heads, run extra checks, debate interpretations, and ultimately expand their understanding of what's possible. Whether it's natural or artificial almost doesn't matter from this perspective. Either way, it's teaching us something new. Now imagine the near future. We've just started detecting interstellar objects with any regularity. The first confirmed visitor was in 2017, the second a couple years later. Now, the third in 2025. The sample size is growing, and as detection capabilities improve, more will come. LSST, the Vera Rubin Observatory, will begin operations soon and will dramatically increase our ability to spot fast-moving objects passing through the solar system. Within a few years, we might be detecting dozens of interstellar visitors annually instead of one every few years. When that happens, we'll get a statistical picture of what interstellar space is full of. Most will probably be mundane, rocks and ice balls that look like solar system objects, but came from elsewhere. But some will be weird. And if even 1% of interstellar visitors are as strange as 3i Atlas, we're going to have our hands full trying to explain them all. That's when AI becomes essential. Human scientists can't manually analyze dozens of weird objects simultaneously, but trained algorithms can. They can flag the truly anomalous ones, the ones that deserve focused attention, while categorizing the more normal ones automatically. They can spot patterns across multiple objects that individual human analysis would miss. So picture 2035, 10 years from now. LSST has been running for years. Hundreds of interstellar objects have been cataloged. Machine learning systems have flagged maybe a dozen as seriously anomalous. Some have weird compositions. Some have unusual trajectories that don't match simple gravitational models. Some show activity patterns that resist explanation. And then someone realizes that these anomalies cluster, that there are patterns suggesting not random natural diversity, but possibly designed characteristics. That's when the conversation shifts. That's when scientific conferences start having sessions on technosignature detection in interstellar visitors. That's when searches for extraterrestrial intelligence expand to include looking for artifacts, not just radio signals. That's when 3i Atlas gets revisited, reanalyzed, recognized as potentially the first example of a category we didn't know existed. Or maybe that doesn't happen. Maybe every weird interstellar object eventually gets explained naturally. Maybe 3i Atlas turns out to be a cosmic noon relic with exotic but purely natural properties. Maybe the AI anomaly detectors flag lots of objects that are just unusual, not artificial. That's actually the most likely outcome, statistically. But here's what's certain. We're entering an era where these questions become routine, where every year brings new candidates for weirdest object, new puzzles that challenge our frameworks, new data that forces paradigm adjustments. 3i Atlas is special because it's happening now, because it's the current mystery capturing attention, but it won't be the last. The universe is large. The galaxy is old. We've barely started looking beyond our immediate cosmic neighborhood. Everything we discover now is sampling from distributions we don't understand, pulling examples from populations we can't yet characterize. Some fraction of those examples will be outliers, natural or otherwise. And outliers are where the interesting science happens. So whether 3i Atlas is a comet, a relic, or something more exotic, it's part of a larger pattern. We're living through the transition from a humanity that knows its local environment pretty well to a humanity confronting the full diversity of what's out there. That transition is uncomfortable. It requires intellectual humility, willingness to revise assumptions, courage to consider possibilities that previous generations would have dismissed. Today's press conference is one moment in that larger transition. NASA is going to show us images and data, offer interpretations, probably raise as many questions as they answer. And regardless of what they say, the conversation will continue. Scientists will publish papers. Amateur analysts will dissect the data. The internet will argue about what it all means. And somewhere out there, other interstellar visitors are already on their way, carrying their own mysteries that we'll have to unravel in future years. 3i Atlas isn't alone. It's a harbinger, a preview of the kind of cosmic surprises that await us as our detection capabilities improve and our sample size grows. The real question isn't what this one object is. It's what we're going to do when the next one shows up, and the one after that, and the one after that. How do we build frameworks robust enough to handle genuine cosmic diversity? How do we stay open-minded without becoming so open-minded that we believe anything? How do we balance skepticism with curiosity? Those are the questions this moment is really about. 3i Atlas is the case study, the example forcing us to confront them now rather than later. And in a few hours, we'll have more data to work with, more clues to follow, more reasons to wonder what else is out there waiting to be discovered. The press conference starts at 3 p.m. Eastern Standard Time. By this evening, we'll know whether NASA's 45 days of silence produced clarity or more questions. Either way, the cosmic surprises of 2025 are far from over. This is just the beginning.